the presenter is David Graupner, and he goes even more wild. So he goes into a situation when system may experience spin fluid, when the spin configuration may change between, let's say, singlet and triplet, or even something more exotic. And David will teach us which specific modifications of the codes and the input files need to be done to deal with non-collinear spin calculations. Okay, floor is yours.
So we're looking at the MATLAB code that we've been looking on. There is a different version for spin orbit coupling, which is the really long MATLAB script type name there. You can find it in the bin on Nurse, at least on Nurse. I think I added both nursing and photon bin, assuming photon's working.
Should be working.
You also need the four master optics, the RRR, the band out, and the energy pop, of which about the last 6 people have all covered how to make. So if we look at the actual input file, you've got these 3 areas that I have boxed. Those are the major things you need to worry about. So the red is the HOMO and the OMIN, OMAX, and those are going to be your orbitals. And you have the blue, the initial conditions, which have been described. So in this case, we're looking at HOMO -5 to LUMO +10. And in the green box, we have some parameters for the Z-axis. The major thing you need to worry about, especially if you aren't worried about getting the dynamics by Z, the major thing you need to worry about is Z steps, because the code will fail if Z steps isn't set up to be equal to the band out with regard to the band out. So then if we look at the results here, so I have, you can see that you get the KH and KE, and then I have the waterfall graph or the occupancy graph, and off to the side here, you can see the code that actually generates this graph. I included the code that generates both the hole and the electron graph, although I'm only showing the whole graph. So the major thing is this waterfall, which is describing the type of graph that it makes, and then the PPE or PPH, which is the population of the hole or electron, which was discussed a couple talks ago. And then here we have the non-radiative dynamics plot, which is the green trig. And then you have, this is the portion of the code that actually generates this plot. So we can see that if we look at it, so the yellow is the value of the electron, with the dotted line being the expectation value of energy. The solid line is the expectation value of energy for the hole, with the blue being the hole, and then the green is the background.
Okay, thank you for being short. Who's joining the thanking David? So any questions, or anyone wants to either give sentiments or challenge the speaker?
I have a question.
Yeah.
Why we need a different set of MATLAB code?
I don't honestly know. I have gone through it a little bit, and all the math I've seen is very similar, but I haven't gone through it entirely to compare them. The major thing that is different is going to be dealing with degeneracies, which I don't know if there's any point in this code that you need to worry about degeneracies. Trying to think through, and I don't think there is at this point.
But your idea is to unify and have just standard release of the code, which will differ only by input parameters, either speed less or speed of the code.
Yes, because I guess we treat competence differently, right? But
Yes.
I guess
Yeah.
how does that?
After that, it's, as far as I know, identical, outside of some minor figure differences
Yeah.
between versions. Which it actually, the figures are really, this version of the code makes doing the figures kind of annoying. You see that the waterfall graphs are actually commented out in this picture. That's because if you have them, the code is set up somehow that if they are in, the code stops after the waterfall graph. It won't generate the green fig or the blue figs. If you have the waterfall, if you have it set up to make the waterfall graphs, and I've not figured out why. I am working on rewriting it to make it a little more streamlined, but I have not gotten to the point where it's ready to actually do anything. I'm also working on adding Aaron's stamping protocol, which Lola used to it as well. And there is some look that it might actually be set up for the 2D orbitals, which I am only starting to work on, so I'm not entirely sure exactly how those work yet.
Do you think you'll be able to show 2D orbitals next week?
I am hopeful.
Okay. And consult London if needed, so he might have some memories of this. London, do you remember how you worked on two-dimensional slices of orbitals of partial charge densities?
Yes, I don't remember all the details, but I do remember, having done it.
Yeah. We need to bring this competence back to group, and David is focusing on it right now. So maybe he will like to contact you, maybe not. So what Dr. Hangout, you will ask David Sparks possibility of effort which goes along from science and more to the business side. Maybe we can make a little, well, it's all non-monetary, but pseudo company that generates a pseudo commercial code. And then we set up a virtual place, like in a cloud or on a server, where everyone has access. And on personal computers, we debug code, but if we see that there is a absolutely necessary change, we just, as a group, co-edit primary version of the code, agree that it will work and matches any conditions, and then announce the release, at least inside the group, and maybe if you want global supremacy to out of world.
So like GitHub,
Yes.
Haley has already convinced me of this, so I believe that it's just here.
Thank you.
Can I answer your question, Julie?
Yes.
Okay. Any other questions?
Thank you. It's more than a question, it's a suggestion. New chapter.
Because I got one, your second slide, you have C half box. Oh, and C step. C sizes, what's C half?
I have no idea what the Z-half does. I've not honestly ever looked through the code to find out what it does. I've never changed it.
Oh, okay, you don't.
David, I have another question, the same question, maybe with 2 lines above. What is the role of this voltage? Always I can see it in the codes, but never use it.
So that, my knowledge adds a voltage parameter, which is we basically never do.
So London and you may answer if they want.
Because it's part of the field variable, which is then used to determine some stuff with energy power. But I've personally never used it.
Amir, thank you for asking the question. I believe you're asking it because you're interested in photovoltaics, or one looks for current as the response to voltage. Maybe it's attracted your attention. So several years ago, London started a project and then did different things, and then Dr. Khan continued. So the dynamics under the voltage shows very different features. Basically, it is all sparked by interest to photovoltaics. And there are two ways to take it into account. One is to literally use electric field in the VASP, so just recompute energetics, like energy orbitals and couplings under the voltage. So in the VASP in car, one can, there is a keyword that adds voltage, like E field equals and then vector of three components. The other thing is to keep the orbitals computed and couplings computed for no voltage, for zero voltage, and then do some artificial correction. Because upon voltage, it just shifts in the first order perturbation theory, it just shifts the energies of each orbital compared to their center of the charge. London, would you like to add something?
No, that's perfect.
Okay. Amir, are you satisfied?
So it is already applied in the codes. So if somebody change just the voltage parameter, it will influence the results correctly.
I think it is just a rudiment as a trace of previous experiments. The version of the code that accounts for the voltage is different and is in a different repository. But if you're interested, it is very possible.
Thank you.
And this half size, right now it is not used, but I think it is done in case one needs to find specific observables for also related to charge transfer. Let's check if there are more questions or maybe typed questions.
Dimitri asks, what are the absolute numbers of HOMO orbitals in NCS SOC calculations in comparison to spin polarized calculations? So the SOC calculations compared to spin restricted have double the orbitals compared to spin polarized. If you are to consider spin beta and spin alpha as different orbitals, it would be the same. If you consider them the same, it would also be double.
So if it is, if one applies it to singlet, then basically HOMO spin orbit will be twice HOMO spin polarized.
Yeah.
If it is like higher multiplicities, it may slightly change by 1 or 2.
Kaya asked David, why did you use IH equals 6 and IE equals 11 instead of using IE equals 6? IE equals 6, you use different values. So is there any reason behind that? I have two possible answers. This was one of the first models I did this on. I honestly don't remember specifics. So it is either the highest oscillator strength or random numbers I picked when I made this originally. If I don't think I have it open.
Okay, let's. Kia, are you satisfied with the answer?
No.
So can you verbally tell what else do you want to hear?
Yeah, like I think it's not a correct. Like maybe it's partially correct that you choose randomly, but obviously there are other reasons as well. If professor explain these things, that will be great.
So yeah, why you think he should use IE equals 6 K?
So this one is from the same model. This is from my Sanibel poster. This is from the same model. This one would be the highest oscillator strength one. So this is, I probably picked numbers when I was screening randomly, and this is what I saw. Because when I made this, I probably was just trying to get a figure that I could put on it originally. But as to why I'm not making them even, it's pretty common for them to not be even if you use oscillator strength as your basis.
Let me add, because if K is not yet satisfied, so in experimental conditions specify only the excitation energy, but the experimental conditions do not tell which specific electron and which specific hole is excited. So what we do, we apply ground state DFT for optical properties, which is not a good thing. It's also a Force-Man argument. It's just because it is so much quicker. In any appropriate methods to describe excited states, the excited state is a superposition of several electron hole pairs. So if we graphically have this much excitation, it can create qualitatively different situations. So first, hole electron, when we remove, create hole on the hole and create electron higher up in the conduction band. With the same energy, we can create a hot hole, or we remove electron, create a hole very deep in the valence band, and create electron on the lumen. Or we create, we can excite in like midway from valence band to conduction band. So if you would base our calculation not on the DFT but on TDDFT or RPA or better circuit, our initial excitation will include superposition of all three. But right now we do need to go over individual excitations. And the question that Kay did ask, I would never ask this question myself. I would just practically, probably reformulate it in the following way. Why don't you scan and show us several initial excitations? Because just to see properties of the system, one needs to scan all of them and see how the system responds to them. But one individual excitation costs nothing, or it's only one demonstration example. To learn more about the system, one needs to scan through multiple excitations. And the symmetric, which looks beautiful for humans when electron and hole are equally deep in valence and conduction band, is only one situation. It is on the equal foot with hot hole and hot electron. Okay, are you satisfied? More?
Yes. Now it's clear.
Okay, thank you. So, more questions today. Questions one, questions two, questions three. Many thanks to all speakers and contributors to discussion. We will have one more knowledge transfer session where we will either repeat some key things or go a little bit more deeper. So we will go deeper into what Amir taught us about charge transfer, and we will open a new little chapter which may go a little shorter in time, photoluminescence, which is a challenging question in itself, but it is another part of the code that we all are already running. So it was just too much for one meeting. And then after we are done with next week, we will be ready for going into more standard practice for all participants of this club. We'll do just research update, and the rest will provide very friendly criticism. So